So another mathematical skill we need to develop when we're working with vectors is to be able to multiply a vector by a scalar. And so for starters, so if we've got a vector like vector A here, where I've got vector A is equal to x component I hat plus y component j hat, so we'll just deal with a two-dimensional vector. So what happens when I multiply vector A by some scalar? So here's the equation that says what I'm going to get, and what this tells me is that so I'm going to get a new vector, vector B, by multiplying my original vector, vector A, by some scalar. And so the first thing is sort of the rule that I use is that both components get multiplied by the scalar. So vector B is going to be equal to my scalar C times AX. That's going to be its new X component for vector B. C times AY is going to be the new Y component for vector B. So my rule in multiplying a vector by a scalar is simply to multiply both components by the scalar. So let's see some examples and then see what conclusions we can draw from that. So what we'll deal with here is we'll deal with vector A. It's going to be equal to 3 newtons I hat plus negative 4 newtons j hat. So it's going to point 3 newtons in the positive x direction. It's going to point 4 newtons in the negative y direction. And so if I want to create a new vector, so there's its components, if I want to create a new vector, I'll call it vector B, by taking this particular scalar, which happens to be negative 1, and multiplying it by that vector A. So my rule says I'm going to multiply both components by negative 1. So my x component for vector B is going to be negative 1 times the x component of vector A, so negative times 3 newtons, that's negative 3 newtons. The y component of vector B is going to be negative times the y component of vector A, so that's going to be negative times negative 4, which is positive 4 newtons. And so what I see is that maps out to tell me that vector B has a x component of negative 3 newtons, a y component of positive 4 newtons, so there's vector B. And it's easy to see, right, when they're both sort of drawn there on the same diagram, it's easy to see how they relate. So clearly vector B points in the opposite direction as vector A, and it has the same magnitude as vector A. Alright, so what if I, again, start with vector A, but create some new vector, vector C. And this time I'm going to multiply vector A by a different scalar. In this case, it'll happen to be positive 1.5. So again, my rule says I'm going to multiply both components of vector A times positive 1.5. So the x component of vector Z is going to be 1.5 times 3 newtons, that's 4.5 newtons. The y component of vector C will be 1.5 times negative 4, so that's going to be negative 6. And so again, when I draw out vector C, positive 4.5 newtons for the x component, negative 6 newtons for the y component. Again, what I see is very clearly that vector C points in the same direction as vector A, but now has a larger magnitude. Let's create a third vector. So here's vector D. And again, I'll get vector D by multiplying negative 1/2 times vector A. So I'll use my rule again. It'll give me a x component of vector D that's equal to negative 1.5 newtons. A y component of vector D equal to positive 2 newtons. So again, when I draw out vector D, x component of negative 1.5 newtons, y component of positive 2 newtons. So I get vector D is negative 1.5 newtons I hat plus 2 newtons j hat. Again, the easy conclusion to draw here is that vector D points in the opposite direction again from vector A, and now it has a smaller magnitude. So thinking about sort of these three examples, let's see what sort of conclusions I can draw. Well, so when I multiply a vector by a scalar, there are two things that basically I can figure out just from thinking about what's going on with that scalar C. So one is, what happens to the direction? And that's basically thinking about whether or not my scalar is positive or negative. So the sign of my scalar C is going to give me information about the direction, how the direction of vector B compares to the direction of vector A. If C is a positive number, then A and B are going to point in the same direction. Again, this is something that we'll come back to time and time again, is if you take a vector and multiply it by a positive number, you don't do anything to change the direction. The new vector is going to point in exactly the same direction as your original vector. On the other hand, if my scalar is negative, then A and B will point in opposite directions. So the sign of my scalar tells me about direction. The absolute magnitude of my scalar is going to tell me about how the two lengths of these vectors compare. So when I'll think about what's the absolute value of vector C. I don't care about sign now, but how does that number compare to 1? So if the absolute value of C is greater than 1, right, such was our case when we said, hey, I'm going to multiply by positive 1.5, then I'm going to end up with a magnitude of vector B that is larger than the magnitude of vector A, and that seems reasonable. Right? So if this is B equals 2 times A, well, that's telling you that the magnitude of B is twice what the magnitude of A is. If B equals 10 times A, then B is 10 times longer than A is. In the special case where C is 1, right, so if that scalar happens to be equal to 1, or the absolute value of that scalar is equal to 1, then A and B have the same magnitude. Third option, of course, is if that scalar C is less than 1. Again, if I take vector B and if I create vector B by multiplying vector A by some number less than 1, then basically what that's telling me is that the magnitude of vector B will be less than A. So if B is equal to 1/2 times A, then sure enough, its magnitude is going to be half as large as what A is. So thinking about what's going on with the sign and the absolute value of my scalar C will tell me about how the direction and magnitude of vector B compares to the direction and magnitude